Okay. Exam 1 is on Tuesday. So here's how this a few things though. Okay, so raise your hand if you finished Jonah. Okay, cool. The I like this story because I'm not going to interpret it for you. But it has some interesting ramifications in the realm of obedience, especially with things we don't want to do. I'm not going to, let's say, do something sacrilegious like telling you what the Holy Spirit wants to tell you about that, because I'm not a preacher. But what I will say is pray about it and think about that. The attitude that Jonah has toward God, what do you think they're supposed to learn from that? Because ultimately the idea is this with scripture. I think what happens is we've hit this point in our culture, especially as Western Christians, that we see the Bible as our bathroom devotional. So every now and then you pop open a chapter, you read it and say, oh, how does God that made me feel today? Blah, 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 you move on, right? The idea is you read stuff because it teaches you stuff. And the idea is that when you learn something, you're supposed to live that thing, right? So live it. You don't have to convince me that you're really reading these things in the word, because ultimately the fruit of what the Spirit is going to do with the time that you give to him is going to be more evident than anything else you could really prove to anybody. Okay, so there's that. I won't assign anything for Bible stuff. If you want to keep reading Jonah up until your exam, that's great, but we'll pick up in Obadiah, I think, next week. How's it going, Josh? You're just in time. Hey, everybody, I want everybody to wait. Stay there, stay standing. Everybody make eye contact with Jock right now. Jock, what is our one mission and what is our one goal?
Our one mission is to obey the Lord, and then our one goal is to worship in what we do.
Yeah.
Glorify God.
Glorify God.
Excellence through obedience.
There we go.
Close enough, now.
There you go. Now you don't have a tardy. You're on time. You've been here. Okay. So we're gonna talk about 14.4. I like this section because it's really easy, and that means you're gonna have time to get out of here early, and that's my goal. Okay.
Go, Scott.
Yes.
I heard. You do like a review day either on Sunday or Saturday.
Yeah. Okay.
Ooh,
That's a good thing.
Saturday?
So maybe what I'll do, can someone rip out a piece of paper and then get it down like a poll? And so write down
Where's that?
the
Got it.
times that you could do an exam review, basically which day and which time on the weekend.
Okay. How long are we looking? Like 2 hours?
Probably 90 minutes.
4 hours.
I will stick around as long as you guys need, but I will make the exam review officially only like 90 minutes.
Wait, so cheat about like what time?
Yeah. So like choose Saturday or Sunday and then vote for a time on those
I
days.
got it.
Yeah. Okay. Let's see. Any other questions about that? What's going to be going on? Yeah.
How was your day?
Oh, it's pretty good. Yeah, thank you.
Did you have any dreams?
Unironically, yes, but it's about some other math thing. So, this is going to be length of curves. And the reason why I'm going to teach you this, I'm going to teach you this in a very efficient way because I'm going to explicitly prepare you for the one length of curves related problem on the exam. How about that? Okay.
Yeah.
So what's going to happen is when you pay attention, you will be ready to solve that question on this exam. That is the sole organization of when I went through these notes. Okay. So you give me just 25 minutes, you're going to get 20 points on this exam. Okay. So here's how this works. In R2, that means 2 dimensions essentially for our purposes. Here's kind of the notation how this works. So we would say, here's a curve C. And then this colon is kind of saying C defined as or such that, depending on how you want to interpret it. There's a lot more nuance the higher you go in mathematics, but that doesn't matter right now. The idea is this is how we can establish a definition for parametrized curve. So R of T in R2, how many are we looking for? How many components basically?
2.
Right. So like we can call it F of T and G of T.
What heading or section is this? Is this 14.3?
14.4. Yes. So if you haven't read through 14.4, you are behind. So try to keep up. Let's see. So then what we do is with a parametrized curve, I don't want this to go necessarily from minus infinity to a positive infinity. So I'm going to get this going from a specific interval A to B. So A less than equal to T less than equal to B. And so what this is going to be is the length of this curve from A to B. So L is going to be the integral from A to B of the square root. It's going to be a big square root kind of thing. And we have f prime of t squared plus g prime of t squared, and then dt. Okay. So just from strictly, here's the formula. I will motivate the formula after this, but I find this, you're gonna want to have an easy reference for this in your notes. So that's why I'm putting it up front. We'll construct this intuitively so how you can help remember the construction of the formula later. But everybody got this. This is so far so good. Yes. I've already noticed that people are dropping off their differentials. So those things matter. Now, it's not going to be something that causes like a 10-point deduction, but it'll count as some point. Okay. And then now, a lot of what we've been doing in Calc 3 isn't really coming up with new concepts, but we've simply extended concepts that we have and make it analogous into one more dimension. So if I have R3, and then I have defined a curve R of t, well, because I parameterized it, how many components is this gonna have? Yeah, it's gonna have 3 components. So we have f of t, g of t, h of t. Notice for vectors, we're using hard brackets. These are not points. Points are different than vectors. So a lot of you guys are using parentheses to designate your vectors. I understand what you're saying, but it's wrong. Okay, so make sure you make your vectors with the pointed brackets and your points designated with parentheses. If you put it in parentheses, I'll initially grade it as if you meant it as a point. And then obviously I won't count for repeated errors. But the idea is get your notation game on, because when it gets confusing later on, it'll be a little bit tricky to differentiate. Yes.
Which bracket should we be using for R naught in the line?
Very good. Okay, so R naught, is that a scalar quantity or a vector?
It depends on when you're talking about.
Aha. So you're trying to differentiate between R naught versus P naught. And that's a really, really good distinction to make. P naught, X naught, Y naught is the description of the point, whereas R naught is the vector that borrows the components. So R naught will always be a vector. Just because it comes from the point doesn't necessarily mean that you have to treat it like a point. So we take that initial point and we're turning that point into the components of a vector. So treat this as a vector, treat this as a point. That's a good. Anything else on that? So then we're missing something here. What are we gonna do? Well, we can bound it, so we could stick it between some A and some B. And then now, what is our length? So is length suddenly a different concept entirely?
Yeah.
No. So if you can do it in 2 dimensions, you can do it in 3. So it's going to be the integral, still from A to B. That's not different. Now, what's the only difference going to be?
We're gonna add h prime of t.
Yeah, we're going to add the h prime of t, and then we're going to square it. Don't forget to square it. So we have the square root, bigger square root this time. And then we get f prime of t squared, g prime of t squared. But now we're extending it one more. We have one more component, h prime of t squared. And what's easy to forget after you write all that down in integral? Yeah, the dt. Okay. So this is it. Like this is the direction and the topic of the entire section of 14.4. Okay. So now I'm going to I'll erase this real quick and then I'll motivate how you can remember this. Because most of you guys are engineering majors, right? Okay.
Question, so does L that refers to the length of the vector, does that mean it's magnitude?
Oh, very good question. Okay. Did I put an arrow over the L?
No.
So is that a vector or a scalar?
Scalar.
Oh, it's a scalar. Okay, so and that makes sense, right? Because the length of a curve, if you're trying to measure the length of some curve in space, it shouldn't be a vector quantity. That's just you're taking its length. That's a scalar quantity. So yeah, so L is meant to be a scalar, and it's going to be a scalar from the way that the formula is. Okay, I'm going to erase the R2 version. I'll keep the R3 version. most of you have at some point probably seen, they'll recall. That distance. Is equal to what?
Square root of x squared plus y squared.
That's not specific enough, sorry, that's my bad, so rate times what?
Time.
Yeah, there we go, so distance is rate. Times time. And so that's something you're introduced to, in high school. And then, you move from the word comprehension to your first kind of like algebraic formula, but as they say, I always call that the dirt formula. Dirt. And I know it works is because I hate physics and I still remember that formula, so. So D equals RT, and now, the thing is, as you go through mathematics, all we're doing is we're saying distance equals rate times time in just increasingly fancy ways. That's pretty much all of this, application. So what's gonna happen is later on when you go to calculus, now instead of calling it per se distance, well, we're gonna have a position function S of t, so we call this position. And then we take the rate S prime, which is V of t, the velocity. Right? In other words, this is acting as the rate. And what happens is when you take those, when you take an integral of a velocity curve, you want the area under, you're accumulating distance basically, because you're getting position, that's the antiderivative. So we get the portrait that distance traveled, so distance is then now the integral a to b of the magnitude of your rate or the velocity. Again, we don't care which direction we're moving per se, if we just want to accumulate the total amount of distance we're traveling. This is like looking at the speedometer versus looking at, your direction. But ultimately, so a lot of people look at this integral and they think, no, there's no way that's related to distance equals rate times time. But what you're doing is you're taking the rate, you're multiplying it by dt. dt is representing time. So really, you're taking a massive sum of a whole bunch of products of rate times time, rate times time, rate times time, rate times time, that's instantaneously changing depending on what this rate actually is. But at the end of the day, you're doing dirt. Okay, so this is just dirt, but now Calc 3 version. So here's your distance, right? And here's a rate, at least the magnitude. And then you're summing it up over time. So you're taking your length or distance, same difference, and then rate times time, a rate times time. This might be tricky to immediately recognize as a rate, but let me remind you of something over here. If I have R of t being equal to F of t, G of t, and H of t, then if I am to take the rate R prime of t, I'm going to have F prime, G prime, H prime. So far, so good. And then what happens is I'm not just interested in the rate, I want the magnitude. So in other words, the analogous idea to just looking at your speedometer. And so the magnitude of this rate is going to be, treat this just like a regular vector. It's going to be the square root of f prime, so the x component squared, the y component squared, plus the z component squared. And isn't that mighty familiar?
Yeah.
That's exactly what we're talking about in our dirt formula, so to speak, but now it's L and an integral and a whole bunch of other garbage. But the idea is, if you think about this in the same analogous sense as the distance equals rate times time idea, it'll help you remember the formula. Because I mean, you could just brute force memorize that, because that's not that difficult to memorize, but you'll have a much richer understanding of why we have that construction, especially with respect to these things. So we could technically rewrite, if we really wanted to, we could re-express this formula as being the integral a to b of what? What could we put instead? Yes, very good, Claudia. So the magnitude of the rate. So this is the formula that's more interesting because it takes fewer symbols to write. They're all important, but they're all saying the same thing. And this is the most efficient way to say it, if you understand what all the different components really mean. Okay, so I'll give you a second to write that down, because what's going to happen is the best way to do these is just to solve a problem through it. And you'll realize this is not as complicated as as it looked.
So that one that you had, like. That one's is equal to the top one then? Or-
Yes, well, because take a look at this. So what does, this is f prime t squared plus g prime t squared plus h prime t squared. All under the square root. Well, that is screaming magnitude formula. Magnitude of which vector? Magnitude of this vector. So that's what I show up here, just so that you can make it make sense for yourself. And then instead of writing out the entire thing, if you understand your definition of magnitude, you can actually condense the entire formula into something much easier to handle at once. Yep. Any other questions on the formula, where it comes from? Okay, let's do a problem. Now, we're going to do a problem in R2. But does that mean it's going to be a different procedure for R3?
No.
No. Okay. So I trust that when you understand the concept and the formula, that seeing a difference in the number of components should not be the reason you're having a deal breaker. Okay. If the deal breaker is something else, we can talk about that. But don't let an extension of the idea to something analogous with higher dimensions be the reason why you're thrown off by a concept. It always just extends it like this. Let's work through this. Actually, let me think how I want to do this. Okay, here's how we're going to do this. I'm going to put up this problem on the board. I'm going to solve it so that you can see what an efficient method, way to get through these kinds of problems. Then we're going to turn to the lab. And then you're going to work through some problems. What I will say is I very, very strongly encourage you to study the example that I'm going to give, because it does a really good job of summarizing the different kind of techniques you'll need to know from the textbook. Because I went through all the examples, I'm seeing what kind of skills you're going to need to know. So everybody write this down. R of t is equal to 10 cosine 2t and 10 sine 2t. 0 less than equal to t is less than or equal to 5. So can you guess what shape this is from your past experience with parameterization?
Circle.
All right, because the cosine is in the x component, sines, and can you take a wild guess what the radius is going to be? Yeah, it's 10. We're taking what we have and we're just blowing it up, scaling it up by 10. And then what on earth do you think the 2 is doing, multiplying against the t there?
Speeding. It's small.
Yeah, so what this is going to have to more do with the way that we're tracing this out, right? Is it going to slow down the tracing or is it speed up the tracing? Yeah, by how much? Yeah, just 2 times speed.
Is that t is less than or equal to 5?
Yes, that's a 5. Sorry, I don't need to rewrite it. So it's kind of like I have to, for Greek exegesis, self-teach myself through a syntax grammar, and then watch video lectures from the author who's talking about the sections. After reading through tediously his entire book, I just slap it on 2 times speed, rip through all the steps so that I'm seeing it all again. Okay, so you can control the rate at which you're sketching stuff out by multiplying constant coefficients by the variable affected in the function. So that's pertinent not just to cosine, but like if you had natural log, and then you add a constant multiplying natural log of 5t, it's going to be 5 times quicker than regular natural log of t, etc. Okay, and then this information is telling you we don't want time to be just this indefinite spectrum from minus infinity to infinity. We start at 0, and I want to run this experiment until t equals 5. Okay? What we're going to do is we're going to figure out how much distance does travel. So how long is this curve in space? So since we're, we're going to have our length, essentially. We need a rate, and then the rate times time is going to come from the integral. So here we can find the rate with simple derivatives. What is the derivative of 10 cosine 2t?
Negative sine 3t.
Minus 20 sine 2t.
Yeah. Don't forget the chain rule, and don't forget that cosine will change sign. And then what about the y component?
20 cosine of T2 cosine 2T.
Just so you are aware, because Calc 1 and Calc 2 are prerequisites for this class. Mistakes on derivative rules that you should know are not going to necessarily be forgiven per se. So know it. Because you don't want to be an expert in the field being paid 60 grand a year and you don't even know your own stuff, okay? So know your stuff, become an expert, that's what you're paying for. And then from here, do we just take the rate as it is? Exactly, we need the magnitude. So if I do the magnitude of my r prime, wow, there was a reason for doing this then, right? Right, so here's our square root. So what's the x component? It's this entire chunk. So we take this entire chunk minus 20 sine 2t and we square it. And then we take the y component, which is this entire chunk. And just plug it in. So 20 cosine 2t and then square that. Now, this is just the magnitude. We haven't thrown it into an integral yet. So we just can simplify this before we actually put it into the formula. And we're going to get the square root. Now, minus 20 squared is 400. So we get 400 sine squared 2t. And then plus 400 cosine squared 2t. A major reason why I also whiteboard out these problems is because this is the style of notation and different conventions that you just need to be doing. So it's like if you're going to indicate that it's the sine function that's being squared, you put the little square right in between the argument. Some people will do this. They'll say sine 2t squared. What's wrong with that? Yeah, t is being squared. So it's not even that the 2t is being squared here, it's just the t that's being squared. Yes.
What if you put parentheses around the 2 and you put the square outside?
Okay, so I mean, if you wanted to waste everybody's time and say sine 2t squared like that, sure.
Oh, no, but what if you put a parentheses between the 2 and the t?
Oh, so you want to, okay, so you could do sine 2t like that and square like that.
Right.
No, because it's square.
No, you're, well, now you're squaring 2t.
That's
Then
4t.
you're 4t. Right. So this is equivalent to sine of 4t squared.
I see.
That's what this is equivalent to.
Alright.
But this is the sine 2t squared.
Alright.
Whereas this is sine 2t, the function squared.
Alright.
So the way we denote, instead of writing this notation, we always just write sine, we put the exponent in before the argument. And the reason why that's really efficient is because then you can communicate a lot of information when you have like multiple powers going on. So like if you had wanted to square the inside too, you could say basically sine squared of 2t squared. So now you're taking the 2t squared inside of the sine and then that entire thing is squared. So that's how you can distinguish between what those mean. Anyways, a tangent, but an important tangent nonetheless. Because the same thing applies to natural log, by the way. So like all of these conventions apply to natural log. So you could put the exponents in the same place. Okay, so we can factor out 400. Hopefully you see that. If you don't, we got other issues.
20.
Right, so we got 400. Now we can take out.
Could we theoretically just take out the 400 entirely, put 20 for the square root of 400?
You could, right now we're just factoring out the identity.
Okay.
So sine squared 2t, cosine squared 2t. Now, do you guys recognize this identity?
Yeah, sine squared.
Yes,
one,
this
sine
one.
squared one.
Right,
'Cause it's
because
the
in general, so the general Pythagorean identity for here is sine squared alpha and then cosine squared alpha, and that alpha could be anything. Yeah, so any scalar valued function inside of there, so long as it's sine squared that scalar valued
Sine
function
squared
plus
theta plus cosine.
cosine squared that scalar valued function, as long as those
So it
are the
doesn't
same,
miss
you
either.
can always.
Yeah, it doesn't matter.
Yeah.
Too. This could be 500.
So then we get
Because
400
1 fast.
Interesting.
times
I'm
one,
like, pretend like I understand it.
and then we're back to,
Yay.
raise your hand if you could do that on your own and feel pretty good about that simplification.
Yes.
Well, that's good. That's good, that equals this, right?
Yes, because sine squared and cosine squared go to.
Alright, yeah.
Okay. And then what we're gonna do is we're gonna take this and we're gonna input it into our formula. So the length of this curve, what's gonna be the limits of integration?
0 to 5.
5, and then here is with the integrand, so whenever we find this right here is the integrand. The magnitude of the rate, and so the magnitude of the rate simplified to just 20. 20 dt. Okay. I really hope you guys know how to do this. If not, basically, this part should not be explained. It is routine at this point. So 20 0 to 5. So again, 20 times 5 minus 0 is 100.
Yay.
Wait, what are we?
That's a nice,
We were not given units.
This is math.
this is a nice.
Math.
This is here.
Oh, yeah.
100 of whatever you want.
Units. Oh.
Could be 100 watermelons.
No, okay, hold on.
Wall.
Just for the record, do you guys know that the British or something, they use like furlongs or something? They got stones.
It's
This is the dumbest thing. I mean, Americans use cheeseburgers and bald eagles to measure stuff, but like,
I measure things like a freedom.
Pugs.
But,
City average
okay,
pug is something like 13
if I were
pounds.
to erase this,
So you weigh someone.
could you solve this problem on your own?
I can now.
Raise your hand if you know you can do it for yourself.
Depending on how many.
You know what my favorite part of math class is?
The liars.
You have the opportunity to prove it here.
So
So it's 127. I'm going to erase the solution, get a fresh piece of paper, start over, solve it for yourself. Get to 100, okay?
Like oxygen sucker. Bullion. You made that? Dude, you gotta do that. It was so funny.
If you want to change the numbers, you can.
I'm gonna do 3 instead.
Yeah.
No.
You don't have to. You can just solve this question right.
We just solved it. Can you do it again?
Once you do it again.
I know. You want me to do it on a different piece of paper? Probably I should, so I'm not looking at it.
And then what's gonna happen is that'll be essentially your ticket to get out of here. But here's the thing, take this time. I opened up lab 2 on D2L. That is going to it's not due on Friday, okay? It's gonna be due, because that'd be mean to make it due on Friday. So what's gonna happen is it's not gonna be due on Friday, but then a week after this coming Friday. So it'll be after your first exam. So your exam's on Tuesday, then it'll be due on that Friday after. Lab 2. Make sense?
Yeah, so next Friday.
Okay.
The exam is just.
Yeah, so next Friday.
Just chapters 13, 14.
13, 14.
And more or less it's covering the lab.